Off you go.
Shall we start now?
Yes, please. Yes.
Good afternoon, good evening, or good morning from wherever you are. I'm Dr. Yao Zhang, assistant professor in maritime engineering at University of Southampton, and I'm also an IEEE UK and Ireland Women Engineering Ambassador. I would like to welcome our audience and speakers to the 11th IEEE UK and Ireland Women Engineering UKI Ambassador Program Early Career Talk. Now I would like to invite Dr. Nagham Saeed to open this webinar talk. Please, Nagham.
Thank you so much, Dr. Yao. So I'm Nagham Saeed, as Yao mentioned. I'm the IEEE Women in Engineering United Kingdom and Ireland Chair. I'm also the early professional lead, the worker group lead. I'm also looking after the ambassador network, and I'm looking now after the publication team as well. So I would like to welcome and thank everyone who's joining our event today, the 11th Early Career Talks, and a warm welcome to our speakers and our audience from all over the world. As I always say, it is a unique experience to witness different talks about the recent technologies and research all over the world in a very short time. So today's talk, we will tackle different technical subjects. That's edge computing, intelligent autonomous systems, generative models, and wireless sensor networks. So our aim is to promote women in technology, as well as creating a culture of diversity and inclusion. We work together to promote junior researchers and improve early profession outreach. So we want to reach out to engineers and the people who work in the computer field, the undergraduate and postgraduate students, and support them as much as we can. So people from academia and also junior engineers, junior graduate engineers. The other thing that I would like to mention is on the 16th of June, the Early Career Talk program achieved its first milestone by hosting the 10th webinar. And we supported directly 40 researchers from academia and industry, that's nationally and internationally. By providing a free platform for them to present their research outcome. We're also proud to provide the online resources later on for researchers. That's via our YouTube channel, by recording these talks and providing them freely on our YouTube channel. And this YouTube channel include these events and much more other online events as well. And this recording will be available as well on the IEEE United Kingdom and Ireland chapter as well. So I'm looking forward for today's talks and discussion, and back to you, yeah. Thank you.
Yeah, thank you, Nagham. So, so this is the agenda of this webinar, and I would like to mention that the presentation recording will be broadcast on IEEE Section R8 YouTube, as mentioned by Nagham. There will be one question for our audience after presentation. So please provide your email and full name in the e-evaluation form if you want to receive your e-certificate, which should be received within 4 working days. And before we start, here are some housekeeping notes. You will notice that you are muted and you cannot use your camera. And if you have any questions that occur to you during the talk and you do not want to lose track of, please do type them into the Q&A chat box. And we will select 1 or 2 questions to let speaker respond right after his or her presentation, depending on the time. And more questions are also welcome, so the speaker will respond to your question via the chat box, or you will be contacted later on via email from the speaker if you leave your email along with your questions. To target the question to the right speaker, please, the audience need write with the question along with the speaker's name or her talk order, namely 1, 2, 3, 4. And so now I will hand over to our first speaker.
Hello everyone. Firstly, I want to share my slide with you. Hello everyone, I'm Shidrokh Goudarzi. It's a pleasure and honor to be here with all of you today. I'm going to talk about optimized edge computing for industrial IoT via UAV-assisted mobile edge server. A little bit about myself. I'm a lecturer in computer science at School of Computing and Engineering in University of West London. And prior to this, I was working at CVSSV lab in University of Surrey. And I have 2 years experience in working on SIGNET project that awarded by US Army and UK MOD. Actually, I received my PhD in wireless telecommunication system and wireless network, and my research area are in wireless network, artificial intelligence, machine learning, next generation network, Internet of Things, and mobile distributed edge computing. And I will talk about edge computing, and I will introducing it to you if you have not heard about it before. In this slide, you can see the outline of my presentation. Firstly, I'm going to talk about major challenges in IoT networks, and then I will talk about edge computing and UAV as a two main solutions to address the existing challenges. And also in continue, I will talk about target tracking as a case study. And then I will share my current research on optimized computing resource allocation in IoT network. And in the end, I will summarize the main point of my presentation. Actually, the main challenges in IoT network, such as automated car, is data processing. And when connected IoT devices generate the massive data, this issue can lead to two main problems. The first problem is that large amount of data should be transmitted and processed through the network, while the computing capacity of each node is limited. And also, a huge amount of data should be transmitted through the network, what wireless and wire resources to offer the requirement of real-time tasks is and to have a low latency are limited. And in this purpose, we need to produce or develop a new model as a cooperative task assignment model to address the existing challenges. And also, this model should be able to reduce the latency through the network and also sensing costs in terms of energy consumption, for example. And in continue, I want to talk about edge computing as a solution to improve the performance through the network with low latency and high throughput data when connected with IoT devices, and can improve the performance. And also, this issue were not possible with traditional IoT. And also, it can be edge node can be connected with industrial IoT to improve the efficiency through the IoT network, and also it can transfer the complex tasks from limited devices to robust edge server. But I should mention that there are some challenges in terms of scalability and also remaining the quality of service through the networks still remains as a main issue in wireless communication. And now I want to talk about some devices that can be used as an edge node. For example, Raspberry Pi can offer the processing power, and they are very suitable option. They have enough memory, and they have a different I/O capability. and they can be applied as edge node for edge computing tasks. And also we can talk about industrial PC. They are very useful in manufacturing, automation, and other industrial application. And they are able to withstand harsh environment, and also they offer extensive I/O option, and they have long lifespan. Now I want to talk about UAV. UAV as a mobile dynamic service. Imaging UAV as a mobile service provider and like a smart helper in the sky. And they can offer different, they have a different attribute in terms of offering mobile service, and also they can play the role as edge nodes. And also I should mention that the UAV are changing games, and they can offer a strong computing ability, and they can improve the performance of network in terms of latency, and also they can empower some devices in the network by offloading the task. And in the end, they can enhance the wireless services and real-time processing. And also, in this slide, I want to highlight the main advantages of using UAV as edge node. They have dynamic computation, and they are able to offer dynamic offloading and distributing computational tasks. And also they can offer real-time processing, and it can be helpful to have a real-time data analysis and decision-making. And also they have a flexible deployment, and they can offer service to other nodes on the ground or in the sky, where and when needed most. And also, they can empower other devices. For example, some nodes have limitation in terms of processing tasks, and they are not available, and UAV can help, and other nodes can send the task to UAV, and UAV can proceed the task and send the feedback to the nodes. And now I want to talk about different strategy. If you check the literature, you can see the different strategy that can apply on the UAV for computing the task. For example, in the first case, I want to talk about a local strategy. In this strategy, entire task should be sent to UAV, and UAV should proceed the task. And in this strategy, we can see the different disadvantages in terms of, for example, high energy consumption of UAV during flight. And also in the second group of strategy, we can talk about local offloading. In total offloading. In total offloading also have some shortcoming in terms of high bandwidth consumption, high computational time, because computation tasks should be offloaded from UAV to ground node, and it has some disadvantages in terms of high computational time. And I want to talk about the better strategy, and we can, after reviewing a different strategy, and we can justify that partial offloading shows a better performance, because computing tasks can be offloaded from UAV to edge node, and then computing results are sent back to UAV. And in our research also, I should mention, we use partial offloading as a computing strategy. And now I want to share with you the target tracking, and this slide. And in this slide, I'm going to talk about target tracking scenario. In this figure, you can see we have a 3-layer. In the bottom layer, we have some static node that deploy randomly to detect the target. And in the middle layer, we have some mobile nodes such as UAV, and UAV can track the target, and we can improve the visibility. And because by using UAV, the blind sensing zone can be reduced based on their flexible mobility. And also in the top layer, we have edge node, and all of the tasks can be sent to edge node, and UAV has a good communication with edge node, and intelligent scheduling decision should be made by a server from a global view. It's just one example of using edge node and UAV in different scenarios, for example, in target tracking scenario. And also in parallel, I want to talk about my current research work. And actually, I work on designing on resource allocation algorithm based on cooperative coalition algorithm. And I could develop a new model for optimizing computing tasks with UAV-enabled edge computing. And in this work, I focus on a scalability issue, and I assume UAV as a edge server on the sky. And as achievement for this research, I should mention that we could manage task computing patient delay, and also we could optimize mobile node accessibility rate. And also we could reduce the energy consumption for UAV and mobile node. And generally, we could meet the task computational requirement. And I want to show you the network model of this proposed model. And as you can see in this figure, we have a 3-layer. In the top layer, we have cloud computing layer, and middle layer, we have edge computing layer, and bottom layer, we have device layer. On the top, we use SCN as a centralized controller, and in the middle layer, we have some UAV, and UAV can contain should be able to proceed the task, and we assume UAV as a mobile edge server. And in the bottom layer, we have some mobile node. For example, one of the ground node is not available to proceed the task, and in this case, each mobile node on the ground can send the data or task to the UAV, and UAV can proceed and send the feedback to the specific nodes. And also, I want to talk about the obtained results. We could compare the proposed model with different model, and we could reduce the computation time and also energy consumption of UAV, and also we could improve the system cost. And as a main objective of this research, we could improve the latency and energy consumption. The proposed model can be applied in different applications. For example, mobile health services, traffic management, remote industrial inspection, search and rescue operation, forest and monitoring, and also smart city management and smart agriculture. As a main contribution of this model, I should mention that in this model, we could address to proceed the task when we have a multiple mobile node concurrently. But in the previous study, the previous researcher, we can see that only one scenario is considered, and for example, they focus on mobile edge server, and that can serve sequentially to multiple mobile nodes. And also, we could design a cooperative or optimization between UAV task execution and mobile node task execution, while the previous study have focused only on one of these approaches. And also, as a third contribution, for the first time, we consider on priority among different UAV processor in computing resource allocation. And also, as a conclusion, I should say that until now, based on my research area, I could focus on designing different type of resource allocation model. And in the current model, I use UAV as an edge server, and I could design a resource allocation algorithm combined with UAV, enable a server to improve the performance. And also, in this model, we consider on scalability in purpose model to handle even large or more complex scenario. And also the finding of this research published in IEEE Transaction of Aerospace and Electronic Engineer Journal. And if you are interested, you can see the paper and each section in terms of problem formulation, simulation, and purpose model or algorithm definitely explain deeply. And in conclusion, I should mention that the journey of optimized computing and UAV-enabled edge computing continues, and in future we can see the novel or innovative application that will integrate more with the technology in our daily life. And in the end, I should say that our task can be more accessible, efficient, and more efficient, and for example, the UAV can play the important role to improve the performance in terms of we can have a strong computational task and more flexible computing task. Thank you very much for your attention. I'm happy to answer your question, and thanks again for this opportunity.
Thank you, Stra. I think due to the time limitation, we've got only one question for you in the chat. So in your proposed model, so how the mobile nodes on the ground can select the best UAV for the task offloading?
Actually, it's a very good question. I should mention that in the purpose model, we consider on the two main problems, distance and capacity of processing the task. And by considering these two parameters as a distance and processing capacity, the mobile node can select the best UAV among available UAV, and it can because the UAV should be able to offload the task and to proceed the task and send the feedback to the UAV. And we consider on processing capability and distance among UAV and mobile node.
Okay, thank you very much, Shidrokh.
You.
Any further questions? Please put it in the chat, and Shidrokh will respond via the chat box. Thank you.
Thank you.
So let's now move on to the second speaker, Shahed. Whenever you're ready, please share your screen. Yes.
Yes, yes. Can you see my screen?
Yes.
Okay. I think this is the best version of this. Okay. So hello everyone, and thank you for whoever joined today to listen to the speakers. My name is Shahed, and I currently work as an MLOps engineer in Virgin Media. And my talk today is going to be far away from MLOps because my master thesis was on denoising diffusion probabilistic models. And as you can see, it's a comparative approach on generative models in art generation. So let me just start with generative models and why I wanted to go with this project. I was so big on GANs. Basically, GANs are generative adversarial networks that are used to generate synthetic images from really large data sets formed with real images in the real world. And I was like, how can I use the new model, which is the DDPMs, the denoising diffusion probabilistic models, and generate art, abstract art, with the same technique that I did with StyleGAN and CycleGAN, and which one performs better? And the target was to generate abstract art using wire destruction-based images. And that was just to emphasize how technology can affect different aspects of our life in a really metaphoric way. So let me just go with the methodology and what I did to go through this and what I achieved. I have a feeling, can you see a presenter mode, or you can see all of the notifications that I'm getting, just to make sure? Yeah, can anyone hear me?
It is in the presentation.
Okay, cool, cool.
Yes.
Okay, so obviously for such an approach, you need a data set. And for this specific situation, I had to create a data set that wasn't existing. And I had to collect abstract art images from the internet and from Kaggle and from different resources, and also war destruction images. And I ended up with a set of 3,818 images of abstract art and 1,800 images of war destruction images. But obviously I had to make it a bit more balanced, so I downsampled it, and I had to get rid of really nonsense war images, like mainly tanks and some tools. And I ended this final data set that I called war to art data set from my own head. After having my data set ready, and I had like a splits for our destruction images, I was ready to experiment the 3 different models that I wanted to compare, which were basically StyleGAN2, CycleGAN, and DDPM, denoising diffusion probabilistic models, with iterative latent variable refinement, which is quite a long name that I'm going to be explaining later on in this presentation. So the first architecture was StyleGAN, differently from a StyleGAN2, differently from a traditional StyleGAN, which you can see over here. There was a mapping network added between the latent vector Z and W, and then this mapping network was connected to some of the features of the generator. Usually, all of the enhancement in generative adversarial networks used to focus on the discriminator model, but in this new version, the enhancement was done or focused on the generative architecture, on the generative model. And I think before diving into StyleGAN or any of the other models, I'm mainly using GANs and the DDPMs. I think I need to touch on what is a GAN. So basically, a generative adversarial network is 2 neural networks. One is called a generator, the other is called a discriminator. And these 2 neural networks are competing with each other to serve the task of generating realistic images from real images. So the generator generates synthetic images based on a distribution of real images, and the discriminator tries to evaluate whether these generated images are real or fake. And this whole cycle continues until you get the generator getting better in generating synthetic images and the discriminator getting even better in deciding whether these images are real or fake. And StyleGAN is one type of these, like of this whole architecture, which is basically shown here. And you don't really need to understand all of the figure, like all of the components of this figure. But just understand that StyleGAN2, differently from a typical StyleGAN, has a mapping network that is connected to the features of the generator. And this helped StyleGAN2 to be better in generating images without an aliasing side effect. Like if you check out some of the images that are generated by the typical StyleGAN, you can see some aliasing and some disformations in the images generated. And adding this mapping network and also adaptive instance normalization layer, the blue ones that you can see here, helped removing that artifact effect. And the second architecture that I also examined was the CycleGAN. And I'm going to briefly touch on this. So basically, differently from a typical GAN, you have 4 different models here. You have an image, you feed it to the generator to create an image Y, which is synthetic. we have another neural network, which is a discriminator here that tries to see whether this image is fake or not. And then this image is fed to a second generator F that tries to reconstruct the original image that was used. So the whole methodology here is based on something called cycle consistency, which is basically a new method in the error function of the neural networks here. And the target is to generate images, but then also be able to reconstruct the original images that were used to generate the fake ones. And that's why it's a cycle GAN. Finally, this is the latest, one of the latest actually, models used in generating images, which is called the denoising diffusion probabilistic model. And if we want to understand how this works, if we look starting from the right to the left, we have a normal image x0 here that is fed to this model, and we start adding some Gaussian noise to this image gradually until we reach a pure Gaussian noise here as xt. And this process of noising the image from right to left is called the forward diffusion. And it's expressed here in the second equation, which I'll explain briefly in a bit. So, okay, now we generated a pure noise image from this original image. The idea behind this whole model is to find a neural network N that can estimate two values, basically the standard deviation and the oh my god, and the epsilon here of the Gaussian distribution. And by estimating or by finding this neural network, can we reverse the whole process of noising to denoising this image and getting a new generated image? And that's called the reverse diffusion, and it's expressed in the first equation over here. And the model that I tried specifically wasn't the first one, wasn't the traditional DDPM, but it was this new one, which differently from the previous model that I've just explained, had an extra conditional value that gives the developer more control on how the model is generating the new images. And you can perform different tasks that are quite similar to what GANs already do, like aging and image translation in different domains. So after experimenting all of these different three different models, I just wanted to see, is this new model performing better in this specific task, or GANs are still the champion in this? So I used two metrics to evaluate my work. The first was the Fréchet inception distance, which is basically a measurement that is used to see how measure the quality of the images generated by calculating the distance, the Fréchet distance between the feature embeddings of the real images and the generated ones. And from my observation, StyleGAN has the lowest Fréchet distance, which means that it generates the highest quality images between the other two networks. The second metric that I've used was a learned perceptual image patch similarity, which basically measures how diverse are the images generated from the real ones, like the real images, and also between each other. And here, CycleGAN got the lowest value, and that means it's the worst. And you can see why it's the worst in the examples that I'm going to show in a bit. And the best one was the ILBR, DDPMs with ILBR, which was the latest model that I've used. And it means that it created really diverse images that are quite different, but still maintaining the structure of the images used for training. If you want to have a look on the generated images, so basically by combining this destruction image with this abstract image using StyleGAN to these are the iterations. Basically, this is the final result, which is quite nice. And I could consider this like abstract art, basically using this initial image as a real one fed. The CycleGAN results were horrible, I can say. It didn't do anything but literally coloring the given image, and the reconstruction was quite good, but like the generated images weren't satisfying the target of this whole process, which is creating distinguished abstract art from the destruction images fed. And you can also look at this and this. It literally just changed the color of the given images. Final results were the images generated by the latest model, ILVR, DDPMs with ILVR. And if you start from here, as I explained, you have like the image, the real one, and then you start noising it. These are images that I got throughout the process of noising. And then the neural network tries to denoise it, but it converts it to another domain, which is like abstract art. And this is the final result. And I'm quite satisfied because it really looks like abstract art, and you would just put it out there without knowing that this was generated from wire destruction images. So the goal that I achieved with this whole approach, I compared the three different models in the image-to-image translation mission. And then I experimented the new model and the new method that is proposed for DDPMs by refining the variant, the latent value. And finally, I generated the targeted abstract art images using the wire destruction images as reference. So that was it. And if you have any questions, feel free to ask it afterwards. Hopefully that wasn't hard to get. And thank you.
Thank you, Shahed. Yeah. So I've got one more minute. So I just there's one question for Shahed is about do we need to have the deep knowledge in generative models to start creating arts or visuals? Thank you.
Thank you. So basically, you don't really need that deep knowledge at the current age, because you have like Mid-Journey, which you can have architects using it to generate some designs and some artists to generate some art based on some prompts that you can find and are quite accessible. So unless you want to create something new or have deep knowledge for your own desire, like you can generate art without having any knowledge about generative models and using some of the already out there services.
Yeah, thank you, Shahed. So for the audience, if I can briefly share my screen, that is a reminder of our feedback form. So please don't forget to fill in the survey using the link here. So I will also put the link in the chat in a minute. And so we can send you the e-certificate, and this will help us deliver better webinars every time. And so once again, please do provide your full name and email, which is essential information for us to prepare the e-certificate for you. Thank you. So I'm now handing over to the third speaker, Yuhan, whenever you're ready.
Yeah. Let me share my screen. Okay, so can you see my screen?
Yes.
Yeah. Okay, let's start. Hello, everyone. My name is Yuhan Liu. I'm a postdoctoral researcher from Eindhoven University of Technology. And it's my great honor to be invited by Professor Yao Zhang to give the presentation with the title, Learning for Predictive Control, a Dual Gaussian Process Approach. And first, I would like to give a short introduction of myself. I got my bachelor, master, and PhD degree from Harvard Institute of Technology. And during my PhD, I was a visiting student in Eindhoven University of Technology. And my research topic includes intelligent autonomous control, learning-based control, model predictive control, and Gaussian process. And I'm a member of IEEE Women in Engineering and IEEE Control System Society. Also, I'm a member of 2 technical committees of our field. And in recent years, quadcopters has found its wide applications in various fields, such as research rescue and taking aerial photos and package delivery, because they are highly maneuverable and mechanically simple. Usually, to achieve a good performance, a precise quadcopter model is required for the flight controller design. But however, a flight control design is not for quadcopter is not a very simple task due to the quadcopter has 6 degrees of freedom with only 4 control inputs, which also leads to couplings in the dynamics, especially during the fast maneuvering task. And in addition, the 10 variant uncertainties and unmodeled dynamics, including such as the blade flapping, frictions, drag force and torques, and also the complex interactions with the environment, such as wind and during the quadcopter is flying near to the wall and taking off and landing missions. These all features makes the quadcopter model quite complex. So my motivation to look into the learning control for quadcopters, because it is very time-consuming and costly to establish a comprehensive dynamic model based on the first principle. So to solve this problem, we would like to find a way to learn the unknown dynamics from the data. And at the same time, we should consider that the system should learn and adapt with the data streaming. And also we should consider the data efficiency and the safety guarantees. Next, let's formulate this problem in a mathematical way. The general nonlinear system can be divided into 2 parts. First is a priori model F, and we can consider it simply in a linear form. And second is the unknown model. It is represented by the G function, and it is usually contains the system approximation error and also the effects that cannot be captured by an idealistic model. And we formulate this issue as a model predictive control problem. As we can see in the left figure, the prediction horizon corresponds to the length of the prediction state and the input sequence. And within the prediction horizon, the system state is propagated by the prediction model. And by minimizing the cost function that penalize the error between the predicted the state trajectory and the desired state reference, we can get the optimized control input sequence. And also the horizon is receding forward the time. And we can see that in the prediction model, there is a G function inside, and as mentioned before, G is unknown and hard to be modeled by the first principle. But the model predict control can only be solved when the G is accurate known, or an approximate description of G can be effectively obtained from data. So such a learning-based predictive control has to satisfy the 3 characteristics. First, to learn the dynamics from data. Second, it has the capability of online update and also considering the data efficiency. And finally, we can reformulate the predictive control with the learned model. First, let's go to the first point. Our goal is to construct a probabilistic model from the system measurement data and to improve the accuracy gradually as more data are collected. And we choose the Gaussian process because it is very flexible and promising to automatically extract the important features of the unknown dynamics from the system input and output data. And GP is completely characterized by a mean function and also a covariance function, and it can be seen as a distribution over the functions. Here is a simple case for GP learning of the sinusoidal function. In the top left figure, we can see that the colored line are the samples from a GP prior space, and also the samples from GP posterior space. And we can see that the shaded part represents the 95% confidence interval, and the red line represents the predictive mean. And we can see that with more data points, which is represented in the blue cross, with the more data points we have, the inference result will be more close to the true function. And the variance, which is the shaded part, decreases with the incoming data. And also for the hyperparameter training, for example, if we have a squared exponential kernel, then we can define hyperparameter set. Then we can optimize these parameters by maximizing or by optimizing the log likelihood function of based on the training data set. So let's summarize the features of Gaussian process. It is a Bayesian non-parametric supervised learning method, and the predictive mean and the predictive variance can be seen as a quantification of the model identity. And hyperparameters are trained based on the log likelihood function without any manual selection. And it is very flexible with noisy data. But standard GP usually suffer from a high computational load, and it is not suitable for large data set because we can see that the standard GP, it is the computational load to train the GP is cubic in terms of the training data set. So it is very so usually it is intractable to retrain or re-optimize the GP when the model changes. So to solve this issue, we need to consider the capability of the online update. First, we focus on the generalization of a sparse variational GP. The goal of a sparse GP is to find a small set of pseudo-points of a smaller size to represent the whole data set. So in this way, we can reduce the computational load, and at the same time, we can preserve the prediction accuracy. And to find the pseudo data set, we use the variational inference. The main idea is to find the distribution which approximates the true posterior of the full training set with tractable Gaussian distribution. So how to quantify a similarity between the two distributions? We use the KL divergence to quantify the distance between two distributions. But we cannot simply minimize the KL divergence because it is analytical. It is not analytical with respect to the hyperparameters. So instead of directly optimize the KL divergence, we choose to maximize the evidence lower bound of the log likelihood. Also, we can derive the optimal variational posterior distribution with the mean and variance. And we can see that computational load is dramatically decreased from the cubic of n to a much smaller value. However, due to the fact that the external environment for a real physical system can be complicated and time varying, and so the offline pre-trained GP model is required to be successively improved to ensure a continuous adaptation. And now, so we propose a novel recursive online sparse GP. We call it ROS GP. This is an online update routine. So we can update the posterior mean and variance together according to the incoming data. And the recursion starts from MU0 and SU0, which can be seen as a prior of the GP, and we can obtain them from the offline trained phase. And one of the advantages of this routine is that we can directly update the posterior distribution. So we do not need to re-optimize the hyperparameters nor update the dictionary at every time step. So now we have an online sparse GP, which can update according to the data and has a low computational load. And can we go a step further to make it more intelligent? So let's imagine such a scenario. Let's talk about the drawback of a single GP structure. Here is a quadcopter, which is learning with large attitude maneuvers, And it is confident to deal with the learned uncertainties with a large data bias because it has the ROS-GP algorithm. But after that, if we start to turn into the next task to hover at a steady state for a while, during this task, it will adapt to its dynamics, and then the knowledge it has learned during the first phase will be faded. So the learned dynamics obtained during the offline trained phase will be forgotten during the online learning phase. So to solve this issue, we propose a novel structure named Dual Gaussian Process. You can see in this figure, this structure allows the storage of the collected experience during offline or historical missions and is able to prevent from knowledge forgetting. And it is a bio-inspired method, just like a human being brain. One part is used to memorize and another part is used to learn new things. And the dual GP includes two parts. First is a long-term GP. It is used to learn the time-independent uncertainties and disturbances. For example, the aerodynamics besides the rigid body dynamics and also the indoor effects. And the second part is the short-term GP, and it is used to adapt with online time-varying disturbances and also the sudden changes in dynamics. And it is worth mentioning that the short-term GP learns around the mean of the short-term GP, of the long-term GP. And to deal with the large data sets, we introduce two sides of the pseudo-pounds of the dual GP. And each GP is specified as a sparse variational GP. This is a simple illustration of the graphical. So how to compute the posterior distribution of dual GP to make the prediction. We also use the variational inference method, and similar to a single GP structure, the true posterior distribution is approximated by variational distributions. And also we can have the evidence lower bound of the log likelihood for the dual GP, which is analytical to solve the variational parameters for the short GP. And if you are interested in the details of the mathematical derivations, please refer to this paper. And finally, given the proposed dual GP structure and the recursive online GP, we can reformulate the predictive control problem. And but due to the stochastic property of the dual Gaussian process, we can see that in the prediction model in the MPC, because G is modeled by a stochastic GP, then the prediction model will turn into a stochastic form. So the GP input becomes a random variable during the state propagation. It will lead to a problem that, so for example, when the GP input follows a Gaussian distribution, it is not a deterministic point. So the GP output will look like a very complex non-Gaussian shape like this. And we use the moment matching method to get the analytical form of the mean and covariance, which means that we use a Gaussian to approximate the true posterior distribution, and we match the first two moments, means the mean and the variance, so can be used for the state propagation. And finally, the state optimization problem can be transformed into deterministic reformulation. And most of the nonlinear optimization algorithm can be used to solve this problem. So next, I will introduce some simulation results of the proposed strategy. Let's consider a quadrotor trajectory tracking task. In this task, we can see that there are some uncertainties and a model dynamics represented by F delta and tau delta. And there are some challenges during the task. First, the ideal dynamics described by the first principle here cannot capture all the unknown internal and external uncertainties. and especially when there are some time-varying disturbances such as wind and aerodynamic effects. And this challenge is tackled by the proposed ROS-GP. And second, it is not clear how the quadrotor can memorize and exploit historical data when the system experiences a similar environment when performing a repetitive task. And this issue is dealt by the Dual GP. And third, the robust satisfaction of the state and input constraints should be guaranteed. And this is tackled by the proposed Dual GP MPC. And first, to construct the training data set, the quadcopter is enabled to track a random reference trajectory and explore the space as much as possible. And in general, the data can also be collected by flying the quadcopter manually. And we use the linear MPC as the exciting input for the quadcopter for 50 seconds and then collect the data with 20 Hz, resulting in a training data set with a size of 1000. And it is worth mentioning that we only use a constant wind during the offline phase to train the GP. And then we test our proposed algorithm. During the online phase, we track a helix trajectory in 3D phase and totally 20 seconds. And the constant wind will turn into a time-varying wind from 10 seconds to 20 seconds. And we can see that the mission of the trajectory tracking is achieved and the tracking performance is adequate good, though the constant wind changes from a constant wind to a time-varying wind. And also the learned unknown function is depicted in the red figure. It is clear that after the second iteration, which means that two tasks with a two-task experience, the predictive mean of the DGP structure can track the true function in real time with a very fast convergence process because the memory of the trained function is kept in the long-term GP. And also, this figure shows a comparative study result. The color of the trajectory indicates the current time. And we can see that both the baseline GP and without any GP compensation and also only a long-term GP has poor dynamics responses during the whole online phase due to their inaccurate prediction model. And in figure C, owing to the recursive online capability of the algorithm, this is offline trained GP with the online update strategy. It shows a relative better performance than the baseline and the long-term GP MPC. And we can see that the figure D shows the best control performance during the entire task. The reason is that the post-dual GP structure enables the real-time accurate compensation of both the system affinities and the time-varying disturbances. And furthermore, the dual GP MPC can preserve the historical data of the repetitive task. So we can see in the first few seconds of the task, it will perform a more precise estimation of the unknown dynamics, and it shows a better performance than the offline trained GP with the online update strategy. And finally, it has a very nice performance during the entire task. And this table gives a quantitative evaluation of the proposed DGP MPC with the baseline controllers. We can see that the performance of the proposed DGP MPC approach dramatically improves through multiple experiences, and after only one attempt, it shows much better performance compared to the other control methods. And let's give a summary of the main contributions. First, the proposed DGP structure is the first GP framework to emphasize both memory and learning ability by a combination of long, short-term GPs. As we can show, such a method can prevent from forgetting, and but at the same time, it ensures the exploration and adaptation to uncertain or varying aspects of the dynamics. And second, A novel recursive online updating strategy for the short-term GP is presented to continuously learn the unknown time-varying uncertainties during the online control operation. And the proposed strategy can update both the posterior mean and the variance, and it's very especially benefits the MPC settings. And finally, the proposed dual GP structure is not limited to MPC, but also can be extended to any GP-based controller which requires additional bio-inspired advantages of both the memory and learning. So that's all for my presentation. I'm open to any questions. Thank you.
Thank you, Yuhan. I think due to the time limitation, I put the questions from the audience in the chat. So if you can please respond via the chat box. Okay, thank you. So let's move on to the last speaker, Dr. Hooman. If whenever you're ready, please share your screen.
Yeah. Can you see my screen?
Yes.
Sorry. What's the problem? Okay. My name is Hooman Sarvghadi, and I'm a PhD candidate at Goudarzi University of Technology. And today I wanted to talk about the new method, decentralized blacklisting method for large-scale multi-hop time-channel hopping networks. This is a short biography. I got my master and my PhD. Sorry, my bachelor and my master from Ismail University of Technology, and I'm currently study PhD in Goudarzi University. Sorry. And the outline, first we start with wireless sensor networks and then go to the IEEE standards 15.4, especially TSCH mode, and then explain a little bit about those blacklisting methods and challenges and the BLUE-TSCH technique. It's our technique that designed for the TSCH networks, and then simulation and performance analysis, and then conclusion. I start with wireless sensor networks. As far as you know, it's widely used in different areas like smart home or smart cities or agricultures or I don't know, other platforms. And if we wanted to categorize the wireless technology based on data rate or range, we can put the LoRa and Wi-Fi for long-range communication, and Bluetooth or Zigbee for the short-range communication, and 4G or 5G or 6G as the cellular networks. And we focus on IEEE 82.15.4 and especially TSCH mode. And the IEEE 15.4 is a specification for the physical layer and MAC layer, and can provide 250 kilobit per second as a transfer rate, or it can support 65,000 nodes, and it uses 16 channels, and it works on 2.5 gigahertz. And if you look at the standard, you can see that the 15.4 use the 16 channels, and it has overlap with, for example, Wi-Fi as an external interference. And if you see that just a few channels like channel 15, 20, 25, and 26 have no interference with, for example, Wi-Fi channels as an external interference, and 15.4 and TSCH mode especially use a hopping method between these channels to escape the noise. And for example, if the channel 17 is busy or as a low quality, we can try for the next time with a different channel. And if I want to look a little bit deep, the TSCH structure, and we has absolute sequence number, ASN, and the total number of time slots that have lapsed since the start of the network. And each for ASN or each, for each 4 time slots, we got 1 slot frame as a TSCH slot frame. And the TSCH used formula as a to select a channel, and it used the hopping sequence list or HSL. And for example, we have a channel quality estimator, and we sense the spectrum, and we find out that these channels are good for our communication. And for example, if we want to select a channel for our transaction, for example, from A to B, the ASN is 0 and the channel offset is 0. The channel offset used for a parallel communication. And in this, according to this formula, the 0 plus 0 is 0, and the mode or the length of the HSL is equal 0, and the channel 0 shows us the index 17. And for A to B communication, we use the channel 17. And for the next time, as you can see, channel 11, we use channel 11. And we can have the parallel communication with different channel offsets. So why we need the blacklisting when we have a noise on our channels or have external interference? And for example, some channels has poor quality, and we have to remove, and we can remove from the hopping sequence list. And for example, as you can see here, just 9 channels are selected to use for our communication, and it helps to improve our communication quality. And the blacklisting methods, categorize the centralized and distributed. Centralized methods usually the sync node or the central node can get the final decision about the hopping sequence list for all the nodes that are in the network. But in the distributed methods, each node can sense the environment and make a decision about the channels that wants to use for the for example, next hop or for communication. And we have different methods like ETSCH as a centralized and distributed methods like label or MAC-based TSCH as a centralized methods. The problem that we wanted to solve it, we assume this network, and we assume that the node 2, 5, 6, and 9 are in the same communication range, and they want to send a packet to their children. And if node 2 and 6 want to send a packet at the same time, sometimes they can use or select the same channel based on this formula. And so if they reach out to the same value as a channel, they packets isn't received or can be lost, or they can interfere. Has an impact to their communications. And these are some examples. For example, the hopping sequence list for node 2 and the hopping sequence for node 6 are different, but in some cases, with the, for example, ASN15 and different channel offsets, they reach to the same value as a channel. And we designed a technique to solve this problem. And the idea is each node has 2 different HSL or hopping sequence lists, and it can design based on 2 things: the eligible channels that each node sends around itself, and have to arrange the channels based on the parents. For example, node 5 should be use the eligible channels like this and arrange the channels based on the parents channels. For example, HSL up or HSL down. When you want to communicate with parents, use HSL up, and if it wants to communicate with their children, use HSL down. And the important things is we use just even numbers as a length of the HSL, and this is the reason. It's a Diophantine equation and mathematical proof that why we use just even numbers. And if this is a Tisch formula, and we can rewrite this formula like this with a Diophantine equation. And finally, with this equation, just only has answers if the, for example, the L1 and L2 is a hopping sequence length should be, or the ratio should be even, and we just use, for example, 4, 8, 12, 10, or 16 as a length of the channel, as a length of hopping sequence list. And we designed some simulations and some different scenarios. With this config, we use the RPL as a routing algorithm and Orchestral as a scheduling algorithm, and use different nodes and use a Wi-Fi as external interference and put in the, for example, no or low, medium, and high, and put them in the, for example, near the sync node or near the leaves. And we try to simulate the TISSIM simulator, which developed at 2020. And this is one of the results for the medium networks with the nodes. And we compare our approach with the TISH. We didn't use any blacklisting methods, and centralized blacklisting methods, and label as a distributed, and BLUE-TSCH, the blacklisting using even numbers that you can see when we increase the interference level, we had a get a higher PDR, packet delivery ratio. And this is another scenario that we put the Wi-Fi sources near the leaves and near the sync node. As you can see near the leaves, the centralized blacklisting methods didn't work because just the sync node sends the environment and make a decision for all the nodes, but the BLUE-TSCH and label has a good performance. But in the near, when you put the Wi-Fi sources near the sync node, the BLUE-TSCH has a good performance, but in most of the cases, the centralized blacklisting methods have a good performance. And this is one conclusion. We described the 15.4 TISH mode and blacklisting methods and interference challenges that we are faced in these networks, and we propose a new approach as a decentralized or distributed blacklisting technique for multi-hop TISH networks, and achieving a PDR above the 90% in most of the cases with BLUE-TSCH, and we make a comparison between different approaches, distributed approaches, and centralized approaches. And thank you for your time and your consideration. If you have any question.
Yeah, thank you, Hooman. There's one quick question for you. So do you have an estimate of the overhead and the cost of your method?
Yes, that's a good question. Maybe I can, maybe I prepare one slide for such these questions. We send a blue packet to update our HSL for each nodes, and this is the propagation packet overhead. This is the length of the subtree minus subtree leaves. And this is got the blue packet. We propagate through the networks, and we have propagation time is we call it blue time. It's rank. It's rank in the tree. If you the RPL tree, and it's multiplied to the time slot duration, for example, 10 milliseconds. And that's it. I hope I can give the answer.
Thank you. And so thank you for all the speakers' presentations. So I just briefly share our slides, just a second reminder for the audience. So if you would like to receive an e-certificate sent by us, please fill in this feedback survey. And I already put the link in the chat. So please do provide your full name plus your email address so we can prepare the e-certificate for you. Thank you. I will hand over to Nagham.
Thank you very much, Anne. Thank you. So I would like to thank all our speakers, and also I would like to thank our audience. I would like to thank IEEE United Kingdom and Ireland chapter section, IEEE Youth Young Professionals, IEEE students, and the IIoT Research Group at UWL for supporting and promoting our event. We are grateful to our sponsors, speakers, and attendees. Of course, I would like to thank Dr. Yao for her help in co-organizing this event. We will continue calling for women in engineering and computing to give technical, inspirational, and empowering sessions. The call for the next Early Career Talks event will be in October, so please keep your eye open. Gertika, you asked for this information, so I'm just passing here the link for this event. The call will be in October also by the IEEE notice, so keep your eye. And here you can see Yao sharing the call as well on the screen. So this is the first event I'm talking about, but additionally we will have many more coming until the end of this year. So please join us if you can. So the other event is Women in Smart Communication, that will be in Romania on the 25th of September. So if you just move to the next one, Yao, and provide the link if you can. Yeah, so this one. So this is just for the attendees who are going to attend the IEEE Smart Cities conference. So if you attend this one, you will be able to join our event. Do you have the links now, or you want me just to drop them in the chat box? Do you have the links for all the events? I can just drop.
Yes, just struggling with managing two screens. So I'm putting all the links in the chat.
Yeah,
I'll reshare
my. She needs my help. No worries at all. Yeah, so the other event, so that's all about this one. This one will happen on the 25th of September, and it is open for the attendees of the IEEE Intelligent Smart City Conference. The other event, which also we are working on and we advertise it by the e-notice, it's gonna be the second career talk, the second Career Development Day at Nottingham University, 4th of October. And this is a call for posters, so you can participate in this event by attending, but also if you would like to submit a poster which is relevant to the theme of this event, please do. We've been working very hard for this event, and I'm sure you will enjoy it a lot. There is also prizes for best posters, so £50 and free IEEE PELS membership. The other event that we are also working on, that will be Women in IoT forum that is a part of the IEEE World Forum of IoT conference that will be in Portugal. We are still working on this workshop, so it might be on the 17th or the 18th of October. So please keep your eye on the e-notice. You will receive more details, and this is also free for the attendees of that conference. The other event we are working on, and also it's free for anyone who would like to attend the IEEE CAMAD. You can see the link as well there. That will be the second edition of Women in Smart Communication. Again, the time and the date is not defined yet. It will be from 6th until the 8th of November. And we will have December time another panel under the flagship conference, the GlobeCom 2023 in Malaysia. And this is also open to all the attendees who are going to attend that conference. That is Women in Engineering panel. Yeah, so that's all from us. We will have a lot of activities, and we hope that you can join some of them. And looking forward to host you again in our future event. Thank you very much. Thank you, everyone. I will stop the recording.
Thank you very much.
You.